All right, so let's take a look at what was it now? Lab 3 with the frequency limits. Now this one shouldn't be that bad. I mean, basically you're taking the the CE amplifier, right, from lab 1, the second lab 1, if you will, and basically varying a few things and coming up with the frequency effects of it and everything, right? Let's take a look. I mean, really, and then varying some values as far as what the capacitors do, and how their effects are on frequency and how you look at the overall gain. I mean, you can even, cool thing with this, I mean, we can even go ahead and actually change our beta value as we go through and determine, oh, does the change in beta actually affect frequency? And it's like, well, I don't know. What do you think? There's my Bodhi plot of the output, right? So if I start at 100, we can see with the Bodhi plot or what the overall response is, right? And I have a 40 millivolt signal going in, just like the directions say. But yeah, you can see as we increase that, right, our response changes, and we start changing our phase. So help you answer that question. And then, yeah, if we change these values in here, let me take a peek. Um, so first, so yeah, so it has, I mean, that's a fair, I didn't think it was that bad as far as being able to look at it. I mean, you basically change the C1 to 10 nanofarad and C2 to a 10 nanofarad and see what the overall effect is. Don't worry so much what the percent of deviation is. And it's like, and essentially, what are we looking at, right? Um, what would resistor and capacitor, what effect could that have on critical frequencies? Well, once you go through the whole lab, um, you can see how that changes things, right? I mean, another way to look at it, I mean, besides looking at the Bodhi plot, of course, is just looking at your overall response of the circuit, right? And there I have before and after the capacitor. You could observe that, and then as you change values and do that kind of thing and pop it around, and as you change and see what it does do to the, like, this amplitude of the signal, the overall response of it. And don't forget, you can change your speed just like in a, like on a no scope, right? So if you need to change your speed, do that so you can see what the overall effect is. um and then really, what do we have here for, there was 3 questions. What effect might resistor and capacitor tolerance have on critical frequencies? So that's your F of C, right? And how do you calculate F of C? So you should be able to come up with an answer. See, the thing with the labs are they're somewhat interpretive. I do agree. But that's, I think, is, so there really is no dead set answer to some of these. And it's the same, like, okay, explain the possible effects of the load impedance on the overall frequency response of the amplifier. And running through the lab, you should be able to see that. And again, I mean, make sure your circuit is working, right? It's like, okay, I mean, I could do a couple of things here if I wanted to verify. It's like, so if we looked at this, and then if I go ahead and pulled this out, and even this one, and then go, okay, what does my circuit do? Does it work? And in this case, yes, it does. See, we have our current flow. So that means that, yes, indeed, this thing is DC biased. So, and remember, we're basically taking the DC, we're taking the DC circuits like we had before. Let me get rid of these waveforms here. See, so there's just my DC bias circuit. So like if we had, actually this would have been nice for the last 8 weeks in some ways, but so here we have, our typical common emitter. And we've seen, if you remember before, when we had, when the emitter was just tied to ground, like how unstable of a circuit that was. And so by putting a negative supply with the resistor as a way to effectively control the transistor, I mean, to make it, I mean, there's still beta dependency with this, and if you've seen, even when I added this in here, right? Let me stop that. You know, varying the value of beta did have an effect on what my signal was, right? So if we observe, it's like, okay, so where's my output? It's there. And then we go ahead and change what our beta value was. What happens? Yeah, you can see there's definitely a change. So now I have changed this, and now I'm experiencing clipping. But let's say we go to the upper limits of the 2N3904, which could be a beta of 300. And so in this case, I mean, now we've literally fallen down below the 0 line. But if we push up, bring it back up to 100 here, now we see a much more, notice that, we see a much more stable thing. And then, so is this circuit beta dependent? Oh yes, very much so. Look at that. So now we've got basically a negative DC shift. So we would have to actually play with the values of our emitter to balance out, right, according to the beta value of this. But if we pump it back up to a stable area here, I mean, we assume a beta 100, and now we got a nice, you know, crossover at 0, 2 up, 2 down. I'm only putting in 40 millivolts, like it said, but sweep through and yeah, take a look at these things. I mean, as far as that, there we go. Seeing what your Bode plot is, so you get your overall response, and even from that, right, changing the beta value, you can see it changes there. Notice it doesn't, I mean, it affects more the amplitude of it, right? But notice there is a slight frequency shift here. Not severe, but there is an effect overall. And that's what it is with this, just to get you familiar with how the RC time constants interact with the circuit. And I think this lab was fairly straightforward. So you should be able to go through this okay based on what we have. And I've been saving these. So when we do the lecture or anything like that, if we need to pull them up, I can do that fairly readily. So, excuse me, call that lab 3 frequency. So like I promised, I'm gonna step through all these and try to record them. And that's really about it for this one, I believe. There